So our mission is to take a 3D point cloud and turn that into a 3D voxel dataset. But we don't want to do that only within Python environment. We'll export our dataset to be usable outside with software like Cloud Compare, Magica Voxel, or even Minecraft. Okay, so bear with me. We go on to this 9-step process that you are seeing here, which have 3 phases. The first one being preparing the data. The second one, attacking how we move from a 3D point cloud to a 3D voxel dataset. And finally, how we prepare this dataset to export it and to use it as an assembly of cube, very simply. And afterward, we'll speak about how it's very useful in the research community, but also for various applications to develop products around voxel dataset. Without further ado, let's dive right in. Alright, so let's start right in with environment initialization. And here we will go on to 3 steps, mainly which is initializing the Conda environment, installing pip, and with that installing various libraries and utilities like IDEs and such. So let me start right off the bat, Anaconda prompt. This is very simple, and then I will just do conda activate visualization. So this is an environment that I already have set up, and in it, if you have nothing, you have to install pip and then install the various libraries that we'll be using, namely NumPy, Open3D, and NetSpy. So for that, very simple, conda install pip, and then you run that, and then after that, you just have to do pip install and the name of the library, Open3D, NumPy, and NetSpy. That's all that you have to do. The last thing that you should do is getting your hands onto a very nice IDE. I like to use Spider, so pip install Spider, and you press enter. And at the end of these various processes, all you have to do is type the command Spider, which will launch your specific IDE. And as you can see, it's already here ready for us to work with. Let's just check where we are onto the workflow. We'll go on to step 2, which is dataset preparation. So for that, usually what I like to do, I will close this, I will open that, is have this kind of organization, having a code folder, a data folder, and a result folder. So in the result folder, for now, I have nothing. In the data folder, I have these data sets, which I can open with an outside software like Cloud Compare. And this is a table that I scanned with my friend Roman Robroek when I was in the Netherlands, which is a very nice Rolduc kind of church. And in it was a very old libraries with a lot of books, a very nice table with a piano. And this is the data set. So as you can see, we'll increase the point size. You have a very cool data set with a lot of books, with a little how is it called, this scaffolding, maybe kind of this piano. And you see that we have some problems because it was acquired with a photogrammetric technique, and this was highly reflective, so I should have fixed that when we shot this specific space. All right, so this is the data set that we will be using. I will just minimize Cloud Compare so that we will check out at the end when we export that everything looks nice and tight. So this is what we have, and in the code folder you have your code. So in this case it's the live that I'm using, right, because I will complete everything live, and that's it. We are ready onto this step 2. Now it's time to go on to step 3, which is creating a voxel grid. So to finalize step 1, basically we just import our library, import NumPy as NP, import Open3D as O3D, and import NetSpy as LP. This is done. For step 2, dataset preparation, we gathered the dataset and we prepared our folder structure. You will find the dataset links and everything with it just down below, right? And now, once all of this is ready, we will just create a path for getting our hands on the dataset within Python, which is pcd_path. So let me save, and here set console working directory so that I can launch cell per cell, kind of in a Jupyter Notebook way. And here I define my path, but then we'll get onto 2 steps. First, we'll import the dataset that is in our folder in this defined path with NetSpy. And for this, it's very simple. You just create a variable. In this case, it will be called point cloud. I use lp.read, and I pass my path to this variable. Next is I will create 2 variables, namely x, y, z, and RGB, which will hold the geometric component of my point cloud, so x, y, and z, and for the RGB it's red, green, and blue. And I transpose that to make it easier to handle, and also I divide it because I already know that I'm on integer 16. Now, this being done, we'll be using Open3D to get quicker with a super cool way to actually trick the library into using it for purposes that it was not defined for. And in this case, we just create a new variable, PCD. We just pass the type of object that we create, so a geometry of type point cloud, and then we will fill in the points and the color. Okay, so this is what we are going to do, and I will just execute. So as you can see, it takes some time, but it's because my computer was on idle. It should not be too long. And on the right side here, you now have the ability to check out the various variables that we have. So the point cloud, which is the last data, the RGB and XYZ. And you have some kind of preview of what you have. So XYZ, RGB. Super cool. Now let's check out where we are and let's go on to step 3, creating a voxel grid. So in here, we will first define a voxel size, right? So you remember that the voxel basically is just kind of a cube, okay? And we will want to represent a point cloud with an assembly of cubes. And to do just that, we need to define the size of the cube, because one cube could be also a voxelized dataset, but maybe we want to go tinier. And I will just showcase what I mean here. Let me illustrate on this, okay? So if I were to put it like this is our point cloud, okay? And I will compute an octree structure on top of it just to simulate this voxel size. And now in it I have my octree. I will just showcase my octree and I will put it as plain cubes, okay? So if I unzoom, this would be a voxel dataset, okay? So this is a cube that holds all the points within the dataset. And if I were to go a bit deeper, you will see that we will have an assembly of cubes that tries to fit better and better the point cloud. At one point, you may have too many cubes, like in this case, when I'm at level 7, my cube is 4 centimeter, and you have around 46,000 or 47,000 voxels, okay? But this is the idea. We want to fit to our data set a lot of little cubes that will make sure that any space that is filled with points will be modeled with cubes. This is that simple what we are going to do. So we first need to define this voxel size. You could just define it straight out of your bat, you know, your data set, and you want to say, okay, my voxel size will be 1 meter, for example. Or you could tune it to the data and make it data driven, so driven by the data. And for that, you could use, for example, the min bound and the max bound of your point cloud and extract some kind of percentage of this as the base unit and use that for your voxel size. So to do that, what I'm doing is actually what I'm saying. So I will take the max value between the max bound and the min bound, okay, and I will multiply that by 0.005 and I will round it to get estimate. So if I were to launch that and check out what we have, it means that our voxel size will be around 3 centimeter. And as we saw here, it's around 4 centimeter, so it will be a bit below. So it looks like it's a pretty sound way to, whichever dataset you want to pass through this little app, it will work pretty nicely. Okay, so this is done. Now the second thing that we need to do is to actually create the voxel grid. And here I'm going to showcase a very quick way to do that with Open3D with just one line of code, which is this one. Basically, it's o3d.geometry.voxelgrid, and create from point cloud. You pass in your point cloud and your voxel size, and you have your voxel grid. After that, the only thing that you are left to do, if you want to extract the bounds, this is something visible with that, but also to draw our voxel entity. This is what we will be getting with Open3D. And as you can see, we now have a dataset that is fully voxelized, and also we keep in the color. So this is highly efficient, especially for Python program. Now, it's up to us to try and move out of Python and move out of Open3D. And this is here where we have to use some kind of tricks to make sure that we can export voxels and also maybe retain some kind of entity decomposition or not, depending on what we want. And this is what we are going to address right now. So before moving there, let's generate a single voxel entity, okay? So as we saw before, one entity in the dataset is a cube. So to generate a cube with Open3D, we first have to pass in the O3D, we create a triangle mesh, we create a box of width 1, 1, 1. So it's a basic unit cube. This is what we'll be using. After that, what we are going to do is also to paint, right? We'll paint our cube with a color. So in this case, I take red, RGB, but in the case of automation looping and trying to extract the full entity, we will actually use the real color that we have. Or we could use something else. This is the beauty of it. And let me, for visualization purposes maybe, let me try and plot that. But before computing the vertex normal. So if I were to execute this, you see that we generate a cube. Basically, the idea is to generate cubes whenever we have point lying within. Okay, so the trick is we will use our voxel grid. So if I take this little variable and I put it here, we see that we have a voxel grid with 117,499 voxels. So it means that we will be creating that many cubes that we will then use somehow. Okay, so it means we need to go into this specific step, automation for voxel generation. So this is the phase 2 in which we are. This is a bit trickier. So you may have to follow very closely what I'm going to explain. It's a bit tricky. The first thing is we will get our voxels. Okay, so for that, to get our voxel, we just create a new variable called voxels, and we will use the voxel grid and we'll just pass in the method getVoxels. Okay, and this will generate basically, so let me execute so that you see. It will take some time, but not too much. Voxels, you have a voxel with a grid index and a color, and basically this is what we are going to use, both the grid index and the color. So to make things more efficient, and this is where the trick lies, we don't work on to the real world coordinate space where each of the points, if I were to open here and just display the point cloud and take a point, for example here, you see that, okay, that's the x is minus 1.25, minus 0.04, and so on. So we are not expressing everything as integer. And this is where the trick lies. In here, what we are going to do is use this grid index. So we are working in a canonical space with a base unit of 1, which is very handy because we can create boxes of this shape, add them together. And the only thing that we will have not to forget is to translate, to scale and translate back to the position, the real world position, our voxelized dataset. I hope I'm clear enough, but let me illustrate hands-on what I mean here. So we have our voxels. Now we will generate a vox mesh. So basically a triangle mesh. It's empty. We initialize that. And the idea is to add each cube one by one to this voxel mesh. And at the end, we have the voxel dataset. So we make a loop, and the loop, I will just write it here. It's a for loop. For each voxel, we'll generate a cube. Exactly what we did. We will paint this cube with the voxel color. Okay, we have the voxel and the color, and we will translate this cube based on the grid index. We don't use any relative position, we just use the grid index. So basically, the cube will have the grid index as a position. Remember that this grid index is expressed through the center, so we'll have, when we will have to do some scaling and translation afterward. Okay, and here what I do is adding the cube to the voxel mesh. And the last thing that we could do after doing that is maybe visualizing this specific mesh. So I do that, it loops, and then this is what we have. So it's actually exactly the same as the voxel dataset, except in this case, we are representing our scene by transforming the center, for example, how you express your voxel based on the center, we express it as faces from 8 different corners or vertices for each cube. The next step, that was a cool one. So the next step is classical normal computation. So here, it's just to soften up a bit the rhythm and go into something that is pretty straightforward, which is computing vertex normal and drawing our mesh so that you can see that you have something that looks pretty nice, especially with reflection or such. You may have a better delineation of the various components in your scene, right? This is pretty cool. Eh? It's like a Minecraft world. You have then abilities, and this is something I show in the 3D Python crash course. You have the ability to turn that into a specific file format that you can put into your Minecraft environment and basically build a massive game from that. Okay. Wow, we are there, and now the next stage is to go on to voxel data post-processing. So remember, the idea here is to export our dataset outside of Python to be used in other software, in other simulation software, game like Minecraft. So here, what I'm doing is a little trick. You remember that we had a cube. Let me paint the cube again, maybe. Yeah. This cube is unit 1, and the voxel, the grid, were expressed based on the center. And doing that, we have a shift of half the size of the cube, which is 0.5. So this is exactly what I'm doing. I'm translating everything back to the position that I want before scaling, so that everything is pretty smooth. And this is the second stage that I will do, is scaling, basically. So to scale, it's voxmesh.scale. All of these functions are not reversible, so once you apply them, they don't create a copy, they work directly on your object, your voxel mesh. So it's important not to make mistakes at this size. So the scale, I take the base point, because now I translate it, so the base point, the lowest left point is 0, 0, 0, and I will use the voxel size to scale, and you remember it's 0.03 something, which means that instead of having a cube unit of 1, it will be 0.0304. So at this stage, we should be pretty good in real-world coordinate, and the last stage that we may want to do is basically to translate. So we'll translate our voxel dataset using the voxel grid origin, if you remember. So if I do that and I put it here, this is my array, and we express that relatively in order to make sure that we don't work in absolute coordinates. And doing that, we have something that is now normally scaled and translated at the correct position. Something that I like to do, sometimes it's not necessary, is because we create cubes, every time we have duplicate vertices at each edge, and here you have a way to delete that. It's not very smart, so it could create some weird geometries or weird faces within your cube, but in this case it will work pretty nicely. And once this is done, all that we have to do is actually exporting our dataset. And here I will showcase 2 exports, and one of which will be useful to work into some kind of software, like maybe not Blender, but Magica, Voxels, or others that I will showcase, which always invert the Z and the Y axis. So first off, let me write a triangle mesh called voxel mesh learn standard.py, and I pass in the voxel mesh. And then the second stage that I will do is actually create a rotation and then export the rotated one. So as you can see, it's basically a transformation matrix 4x4, where the first 3 are define the rotation parameter, and the last 3, so the last column is the translation, and the last number, this one, is the scale. So in this case it's 1, but it means that we want to keep the x-axis as it is, and here we invert -1 and 1, which will apply this specific rotation. So keep in mind this matrix if you want to use that outside of classical software. So now I can open my result folder, and as you can see, it's empty. So let me first okay, so I made a little mistake here. Let me bring that here and bring that, yeah, here. So this is the post-processing. The post-processing is now done, and we move on to voxel dataset export. And in this case, these are this line that I just wrote, and when I press enter and open my folder and press refresh, we have our 2 dataset. So let me take them and drag and drop them in here, and as you can see, things are pretty smooth. So we are our scan table, right? This is our table, and now we are our mesh with the colors that is generated by our little Python program. So this is very cool. And the second one, this is the rotated one that will be useful whenever you have problem in your software, and I will showcase that just right now. So you have the ability to go on to ftracy.github.io and download the magical voxel viewer. Nothing to install, it's just a folder like this one, And in it, you have the ability to drop into the model. So let me delete all of that. You have the ability to drop in to the model some kind of file format, which is either Vox. So here I don't go too deep into the Vox file format because it's a binary one. I want it to work with open standards. Just that it does not read directly the PLY file format that we exported. So you have two ways: either you convert it within Cloud Compare, or you export it again from here, but as OBJ. OBJ. Let me do that right now. Yeah, we'll not have triangle normals, but that's perfectly fine. So now what I can do is open up my result folder, and we now have the OBJ file format. You see that it's much heavier because it's not compressed as the PLY is. And basically I will just copy that and paste that into my model folder in here. And now in the magical Voxel viewer, I will just open the viewer. Maybe I can make it full screen. I go into OBJ, and you see that I have two files. The first one being the standard that I rotated. I think I mismanaged something, but this is perfectly fine. So as you can see, yeah, because I applied 2 times the rotation. This is why. Okay, this is what I mean in here. Very good, because here it illustrates what I meant before. Every time you do an operation on using merge, translate, or applying the transform here, you actually modify your object. So I made a rotation and I made the rotation back, but this is fine. Yeah, so this is what you get, you see, and this is very cool because Magical Voxel allows you to make some kind of rendering. You can also adjust the level of detail. So let me showcase what I mean here, right? You could go lower and have something a bit lower, a bit like in Cloud Compare, but here with nicer ways to manage how you render things. Like in here, you can showcase the edges, for example, to have a cell shading kind of way. This is just a small bonus that I wanted to showcase, that you can work outside with what we just created. The last stage is maybe thinking about other approaches or perspectives. And very quickly here we used Open3D, but you can do that all with only NumPy. And here this is a small example that I created. The only thing that I'm doing here is exporting the center point of each voxel, but I just want to showcase that it actually runs with the same, if not a little faster. And in my result folder, we now have the voxel base point. And if I drag and drop it here, apply all, we should have something which is exactly on top of our dataset. And you see that it's much more regular. So why is this so useful? What are the perspectives at this stage? This is very important to understand, that having the ability to voxelize your point cloud is huge, because aside from moving in from a specific way to represent the data to another way, it means also that you can get onto other algorithm, other ways to process your data. And let me give you a very clear example. The first one being, it's very often that you need to sample your data set. And with Voxel, you can sample by being very, very regular into the spatial decomposition, because you use base unit, like what we had 0.0304, and basically you could generate or keep the point closest to the buried center that we see here of each voxel. So this is a subsampling strategy, but you have also the ability to use this structure to extract. So if I showcase here, you have the ability to use this structure to extract relationship information. So this is a wireframe. Let me just showcase without normals, and maybe without normals. You can extract the relationship information, if it's adjacent or not, for example. And this is very, very useful for connected component labeling, or thing that plays heavily onto the data structure. And another thing that is super useful is to actually transform any of your data set into Voxel dataset to apply convolutional layers, like with pixels, but in 3D, right? You make layers and you apply convolution, which makes it much easier to get onto 3D deep learning. If you want to get very deep there is a course at the Academy that targets specifically how you go from point cloud to Voxel to using 3D deep learning for semantic segmentation and classification tasks. But yeah, these are 3 examples, and a lot of other examples comes to mind, like for feature computation, if you want to to also grid your dataset and split it in various tiles. This is could be done with Voxel approaches or Octree leveling approach. So there are a lot of possibilities. And you have a way now to turn 3D point cloud into 3D voxel with a very cool little program using only Python. So this is super cool. It's only the first stage, as we saw, to go onto very deep application within 3D data processing, 3D fit AI, and a very cutting edge technology. If you like this tutorial that gives you value, that's my goal, and I'm very happy about it. If you have some ideas or some challenges that you are stuck with, please leave a comment below about what you would like me to work on, and I will make my best to try and unlock what is a bit complicated around this 3D data science, 3D fit AI field. I had a blast, I hope you did too. See you in the next tutorial. Bye bye.